Welcome everyone to this new episode of the podcast Coffee Breakdown. I am Luca, and today we have a new guest who's Professor Savino Longo. Savino is a full professor at the Department of Chemistry at the University of Bari. And during his career, he worked on many topics related on computer models for plasma physics and chemistry, astrochemistry, astrobiology, and in general about complex systems. So thank you very much, Savino, for being here.
Thank you.
So first of all, well, I'm very glad to talk with you, and I would like also the general public to know about you. So can you tell us when you became interested about science and how?
In fact, I remember that I became interested in science very early, very early, because already when I was, say, 7 or 8 years old in school, I don't know why. We started to make, some experiments. I remember that with my friends, especially with the very good friend of when you are very young, we started to make experiments on how you get different colors when you write with pencils with different colors on the same point. So you add, for example, green and yellow, and you get another color, or you get black. And there was some connection with chemistry. Okay. In fact, I started to be interested in chemistry from when I was very young, and then it was strange because I devoted many years in the conviction that I was much interested in other sciences, and I studied a lot of mathematics, and I graduated in physics, and then after say 30 years, ultimately I became professor of chemistry. Okay. So it is very strange because it is like chemistry was there from the very beginning, but I arrived there by a very long way.
Okay. But probably it's the combination of the knowledge of different sciences that makes it also more complete. You know, you have a vision that is more complete than only a chemist, the people who do just chemistry, since you studied also mathematics and physics and so on. And I think this helps a lot.
Yes, this helps a lot in formulating sometimes a new idea. Mm-hmm. In Italy, regardless of what people say, especially publicly said, this is not very appreciated because they prefer specialists. But of course, I can do nothing about it. You are right. I am what I am. So. I like to work with the specialists of different topics and formulate transdisciplinary proposals. Yeah, I always do this. And but students appreciate it a lot. Students appreciate it a lot. And sometimes when you get an idea which can be actually pursued seriously, cross-disciplinary is something which add value because when you are at the boundary between different disciplines, it is even relatively easy to say something new. Maybe it's not very relevant, but you don't have the focus of the others, of your colleagues on you. So sometimes it is difficult that it becomes de facto important. It takes time. But when you are in the boundaries, really, it is really relatively easy to say something new. So this is an advantage.
Yeah, but you can give also a new perspective, to people working in the field, coming from another field. I think that's nice. Yeah. Also, what are your hobbies, outside science, basically?
Hobbies from the very childhood, I was interested in astronomy, amateur
Astronomy.
astronomy.
Okay.
Now is maybe is almost more than 40 years. I practice amateur astronomy. I am part of groups and we deliver seminars and also stay sometimes in the night in places where you can see the stars. And other people, not me, other people bring good telescopes, relatively powerful telescopes, and we look at the stars. Now it became very easy to make pictures of the stars through the telescope because you know of smartphone technology. In the past, you have to buy a camera to do photo. Now it is very simple to do astronomical photographs, and of course, it is also very, very easy to share them. So it changed a lot. It changed a lot.
Yeah, because of the advancement of technology, I think, right? In photography, as you said, that's true. Okay, coming really into science, one of the reasons I wanted to invite you really is that I think worldwide, I think you're one of the experts of low temperature plasmas. So in this podcast, we already had some episodes about fusion plasma. So can you explain us what is a low temperature plasma and what is the difference between a fusion plasma and a low temperature one?
Okay, plasma, people sometimes say it is a fourth state of the matter. The other three states being solid, liquid, and gas. You know, this is a kind of abused definition, especially because for other specialists, other states of matter are the fourth state. For example, people in liquid crystal believe this is the fourth state. People working with complex matter on smart materials, which are strongly organized, sometimes they say this is the fourth state. So there are many candidates for the fourth state. But what is in fact plasma? Plasma, you know, is a dangerous word because people immediately think to another kind of plasma, which is the plasma of biology. In fact, there is a connection in terms of the meaning of the word, which is the reason why both of them are called plasma.
Okay.
For me, plasma is a gas, which is ionized, which means you put energy into it. You put energy. You can do it by heating it a lot, like in the sun. And so it becomes a high temperature plasma. And you have ions, you have electrons. In fact, molecules break up. Atoms become ionized, so they break. And it is because of the high temperature. And this is high temperature plasma.
Yeah.
But when you produce the plasma in the laboratory by using an electric discharge, it is possible, it is actually very easy to produce a state of the matter where electrons, which are small mass, so they move a lot, they move faster, electrons are hot, while the rest of the gas is not hot, it is room temperature. So this is not like the sun. This is more like light sources which we use, which very often are, if they are not LED, very often they are in fact called plasma. And this is the state of the matter we are mentioning. So it's a gas where you have a lot of electrons, not really a lot. In fact, even just a few of electrons make the difference. Normally, you don't have electrons in liquids, for example. You have negative ions, like in solution, which are, basic. So you have negative ions formed by water, but they are not electrons. Electrons are very rare, but in cold plasma, you have an important fraction of electrons, and they are very hot, while the rest is cold.
And this is also where the connection between physics and chemistry come. In this type of plasma, you can have different species also in different quantum states, right? And you have to take that into account sometimes when you do your computer models, I think.
Yes, yes. For me, it is much a matter of computing. In fact, cold plasma, if you want to describe them by a numerical model, they require physical knowledge, mathematical knowledge, computer science, of course, but also chemistry. I would like to mention that, in fact, this is especially for me and for people who do computer model of plasma, but in fact, cold plasma has a natural connection to chemistry because it's a low temperature way to put a lot of energy into the molecule. So, for example, you can produce a lot of radicals. A way to produce a lot of radicals is to heat up the gas a lot, but then you cannot use this gas for many applications because it is hot. So you can, it cannot touch, for example, biological tissues. It cannot even be stored in glass because the glass would melt. So there is a natural connection.
Yeah,
Cold plasmas are very important for chemistry and also for medicine, biology, and material science.
Yeah, so some of the application of these plasmas, in fact, is, you know, the interaction of the plasma with the substrate or surfaces that are like biological tissues and so on, or like for semiconductors. So recently there have been also applications in the field of green energy and so on. So you worked also on this topic. So can you mention something about that? And how can low temperature plasma be exploited for environmental applications?
Yes, this is an application which started a few years ago. In fact, there were precautions. There was considered a lot and studied a lot in the former Soviet Union, and it was 30 years ago, but then it was kind of forgotten. But before, it is better than I say what I'm speaking about.
Yeah.
The idea is to use the special reactivity of cold plasma, which is cold, so, but it has these high energy electrons, and these energy electrons get their energy from electrical power. And you know that electrical power now can be produced very effectively as by renewable sources. So in principle, if you apply electrical power, you are on the way to a green application. So these electrons can have high energy because of electrical power, but they can, for example, break molecules. And by breaking molecules, you can remove from existence molecules which are noxious, molecules you want to be something different because they are made of atoms. You cannot remove the atoms.
Yeah,
but
so
for example,
molecules
CO2.
Exactly, okay.
Yes, for example, CO2. Okay, CO2 is a harmless molecule. You know, it's not toxic. In fact, okay, if you have a lot of CO2 in an environment, this is not good, but technically it's not really toxic or even less poisonous. But you know about this greenhouse effect, which is enhanced by CO2. Now CO2 became a molecule you want to transform into something else. But the problem is that the CO2 is the product of combustion. So it being a product of combustion, it is a very stable molecule, because to get the CO2, you obtain the energy before. You have a lot of energy in methane, you have a lot of energy in wood or in coal, especially, of course, when you have also oxygen, and then you can get a lot of energy. But after you get this lot of energy, what remains is very poor of energy. So CO2 is a molecule, let us say, without chemical energy. And so it is very stable. It will never react to become something else, and it accumulates. Okay, plants are able to transform CO2 into oxygen. And we would like to do the same. And people do this, for example, try to do this by using artificial photosynthesis. It is a very important subject. But another possibility is to use a cold plasma.
Okay.
You put the CO2 into cold plasma, and these very, very fast electrons break the molecule. After you break the molecule, you get something which has high chemical energy, and so you can transform this, in principle, you can transform this activated CO2 into, I don't know, fuel back, or you can transform into plastic, or, you know, drugs, whatever you want, in principle. Yes.
Yeah, so really the idea is to capture, you know, the CO2 out of the air, right? And to break these molecules and to convert it to other chemicals, in fact, that we can use in industry and transportation. So then, of course, we can break the molecules in many different ways. As you mentioned, we can heat up the gas as simply, or we can use a plasma and so on. So in this respect, what is the uniqueness of the plasma? Is really to enhance chemical reaction in this case, to activate molecules.
You know, plasma is an option.
It's an option, yeah.
Science, in my opinion, has the responsibility to produce options. Then is it up to the political planners, to economic planners to decide, but they cannot decide if they don't have an option. You know, you need to know several ways to solve a problem according to science, because you cannot ask a science to solve a problem in the urge of application, and even less, even worse, in the urge of emergency.
Yeah.
So if we need, let us say, 20 years of research to imagine, to produce a practical way to eliminate CO2 by using plasma, we must do it now, so it can become an option in the future. In this respect, why dissociation of CO2 by plasma is an option? In principle, the best way to remove CO2 from the atmosphere is to use a natural photosynthesis. So you plant a lot of plants, a lot of trees, and this is the best solution. Okay, this is the best solution. But there are problems in this, in pursuing this solution, because, for example, we really have a problem of locating wide areas which can be populated back with the green plants or with the trees.
Yeah, I've read some papers. I've read some papers that were calculating the area in the world that we need to, you know, replant or grow more trees and so on in order to reduce the CO2 amount from the atmosphere. That is really a huge area. In fact, it's possible. It's possible.
It's possible. Yeah, in principle, it's the best solution, but most of the areas cannot be used. They are used, for example, to produce food. So you cannot convert back to forest. Most of the cultivations which are used to produce food do not have very effective green leaves. So you either produce photosynthesis or produce food. There is not necessary connection. And most of the areas cannot be used because they are in the mountains, or you don't have water. So plasma has an advantage. Is an industrial technology. So industrial means that you can do a lot of product with a small area, because it is a high efficiency, high yield. A future plasma reactor to dissociate the CO2 could be as effective as a huge forest of trees. But of course, you need much less area. So this is the advantage.
Yeah, one thing to mention, I think, because when we talk about plasma reactor, maybe people listening this episode think, you know, we need a huge power plant, like fusion reactor, but it's not the case. So these devices are kind of limited in size. Is it correct?
Yes, no, they would be essentially like a normal chemical factory, and they would use in the ideas renewable energy. All electrical. They are all electric. So then it is up to science to find a way to produce all electrical energy in a green way. But this is a problem we must solve in any case. So we must assume that the problem will be solved. Then after we have green electrical energy, these factories would use this green electrical energy, for example, to convert back CO2 to fuel. Yeah. Which means, this is a very big advantage advocated by many specialists, that you could, in principle, in several states, which cannot actually opt for all electric, they could still use the present technology for transportation, for example, which is using basically chemical fuels, and then out of this circle, you produce back fuel. So you have vehicles working, for example, with ethanol, but this ethanol is produced from CO2. Yes, and from
so it's a transition technology.
Yes, and of course from water, of course, because you need hydrogen. But then water is completely renovated in the circle, in the full circle. So this is not a problem, because a combustion produces water again.
Yeah, and also mentioning other types of application. I mean, not related to CO2 or green energy. So in the future, in the coming years, which type of new application do you see it coming, or that are important, that may be important?
You mean for plasma?
Yes.
Okay, I would distinguish between application and science.
Okay,
because, plasmas, for example, plasma are bring very interesting scientific problems, and by solving this problem, we can learn a lot. In fact, plasma are inertial. In fact, you have plasmas in thunderstorms, you have plasma in stars, you have plasma in the ionosphere. So you can believe it is a smart application or not, but you cannot get rid of plasma. And by studying plasma, you develop new ideas, and from new ideas, you get application. Yeah. But in terms of application of the plasma as such, now I see my colleagues working a lot in a lot of different and promising directions. For new directions, really new, I mean something which was barely mentioned 20 years ago, like, for example, to use plasma in medicine to improve, for example, all the technology which is used in surgery, or even to heal some illness. And in agriculture, it was found that if you expose, for example, seeds, not any kind of seed and not in any condition, but if you expose seeds to cold plasma, then you can get, for example, products which are much less susceptible to, for example, to the attack of mushrooms, of bacteria. Mm-hmm. They decay much slower, and you don't use any chemical product. And also other applications, so for example, are in chemical synthesis, because we have seen that in plasma you can produce a lot of radicals. From radicals you can produce almost any kind of chemical. Plasma is already used, for example, to produce ozone. Anyone knows about it. Ozone is important because you can use, for example, to clean water, to clean air. You can do a lot with ozone. And in these generators, ozone is produced via plasma.
Yeah, very interesting.
Ozone is an example of chemical produced by plasma, but now we have seen that we are discovering that many other chemicals are effectively produced via plasma. For example, it is possible to fix the nitrogen in our atmosphere and convert it into useful chemicals by using plasma.
Yeah, and again, this is something that biology does it, naturally. for example, plants for fertilization and so on. So they break this nitrogen, but we can also do it artificially using a plasma.
Yes, no, they do it their way by using catalyzers, which are organometallic molecules. It is like this matter of artificial photosynthesis is an option. Yeah. You can fix nitrogen, for example, by using a natural way, or by using the methods actually presently used in the chemical industry. Plasma looks like a very interesting option, especially if in the future we will have a lot of electrical energy produced by sustainable sources. If electrical energy becomes the most important, starting point for green application, then plasma becomes much and much more important. Because at the connection between matter and electrical energy, you have plasma.
Yeah. So coming back to a bit more theoretical, numerical, so which type of models do you use to describe the chemical reaction and the discharge in general, the plasma in general?
The models are very nice because they are used on some mathematics which sometimes is not elementary. Mm-hmm. So you have the possibility, in fact, to practice some quite advanced mathematics and good computer science. You need, now it is difficult to say here how they work, but they are, structures. They are mathematical structures. Mm-hmm. Mathematical structure means you have something which is ordered, and it may change. A mathematical structure is a very versatile concept. There are special words to call. Sometimes, for example, they are technical terms. Most people, of course, will not understand them. But for example, sometimes a chemical structure in what specialists call a differential equation. Mm-hmm. Sometimes a structure is a matrix. Sometimes a structure is another group of numbers which is connected by pipelines, abstract pipelines, and numbers are able to move from one part of this structure to another part of the structure. What I mean is that this is sometimes this is very abstract mathematics, or in any case high-level mathematics. Yeah. But then you must use it to write a computer program. So you need also computer science. After the computer program is able to produce numbers, and these numbers may become plots. And looking at the plots, and this is the ultimate results. One hopes, from this plot you get the insight. So it means that then you need human imagination. Mm-hmm. So
again, it's really multidisciplinary. So you need to know the physics, you need to know computer science, mathematics, and so on. So it's not easy, in fact. So
it's not easy because it is hard to find someone who has studied this kind of topics altogether. So, for example, when I have a new student for thesis, and it was also my case when I was young, if you want to work in this topic, you learn that if you are, for example, a physicist, you don't know chemistry. If you are a mathematician or a computer scientist, you know a lot, but you don't know why. And so you have to understand, and you don't know how also. And so you have to study. In fact, now this kind of science, when you have mathematics together with the computers, with the physics and chemistry, and is becoming much more known. And there will be more of this in the universities in the future. But now it's still like this. I have, for example, students who want to do their master thesis with me. If they are chemists, they know why but they have to learn a lot of mathematics and computer because they start working.
Yeah. Now, like going a little bit more technical, can you explain maybe in simple words what is a Monte Carlo method? And now this method can be exploited to study plasma in general.
Well, Monte Carlo is, you asked this because you know, and Monte Carlo
Yes.
is a kind of one of these structures, one of these mathematical idea which you can use in order to transform ideas into these numbers or plots. Monte Carlo is a technique for numerical simulation, for computer simulation. Simulation means that you have a model of the phenomenon, which is something which is mathematical, but in some respect is similar to your phenomenon. In plasma, for example, electrons are moving in any direction, randomly, and they randomly change the direction in which they are moving. And so this random element can be introduced in a computer program by mathematical structure which are specially able to simulate the random chaos, of the real world. They are called random number generators. So they are simple formulas which produce numbers which looks like to be random. The idea is very old. This idea dates back to, in some respect, I mean, not complete, not exclusively, but it comes from the studies for the production of the first nuclear weapon. So Los Alamos, Los Alamos project. And there were some mathematical studies connected with this, mostly by von Neumann, anyone knows von Neumann, and less known, but very important here, but not mathematicians know, is Stanislav Ulam. Stanislav Ulam may be much less known by the general
Polish,
public.
I think it was Polish.
I think so. He wrote, in fact, a book which is very famous about the experience of working as a mathematician, which you may find in bookshops, but is much less known. And he was the person who devised the name Monte Carlo, because in Monte Carlo you have casinos. And so you have roulette, and you play with the cards, blackjack, but whatever. So Monte Carlo is like random, and this is the idea. This is why it was called Monte Carlo method. In fact, it is very there is a funny story about a variant of the Monte Carlo method, which is much less known, which is much less used, and I believe that in time it came to merge, in fact, with Monte Carlo method, and it was, for the same reason, it was called Las Vegas method.
Okay, that's interesting. Yes, another topic I would like to talk with you is something probably not so well known, at least not from my side. That is astrochemistry or astrobiology. So I'm used to hear, I have a background in physics, so I'm used to hear astrophysics, but astrochemistry is difficult for me to relate. What is astrochemistry? What is astrobiology? So what are you studying in this field?
I am studying a lot. I have been studying astrochemistry for many years, and now I have an interest in astrobiology. This is a very long story. In fact, I am not even sure that astrochemistry is an appropriate name for the discipline, because what is astrochemistry? Astrochemistry is the study of a chemical reaction which happens in space. So they are very important because, of course, in space, you may produce, for example, molecules which are the molecules of life. And for people interested in the origin of life, is not immaterial to have information about the possibility that amino acids, sugar, even components of the ribonucleic acid can be synthesized spontaneously in space. And this is astrochemistry. So in fact, the term is not very fortunate. Okay, it has a lot of fortune as a term. It is used a lot now, but is probably not the best, because you know, astrochemistry is not a discipline in opposition to astrophysics. Astrophysicists knew a lot about astrochemistry even before, because the chemical reactions in space are important for astrophysics. In fact, astrochemistry was devised as a term, like to say astrophysics is physics of space, astrochemistry is the chemistry of space. But in terms of etymology, astrophysics is not the physics of space. Yeah. Astrophysics is the understanding of the space object, opposed to just a description, which is done in astronomy. So it's the physis, like in ancient Greek. Astrophysics is the nature of the object. What is a star? This is astrophysics. So in fact, astrochemistry is not in opposition to astrophysics. Yeah, but now people call it astrochemistry, and I am happy about this because it is a corpus of knowledge which needs recognition. You must be able to address immediately what you are doing. So I am happy that you have this term, but in etymological terms, in my opinion, is a little misguided.
Okay, yes. Well, also it may be important if when, you know, sometimes we hear this discovery of exoplanets. So to address the question whether life can be formed in extraterrestrial planets, for example.
Yeah, this is astrobiology.
This is astrobiology. Okay.
Now, you know, astrobiology is a very, very new term. Just a few years ago, it was not used. It sounded very strange. But in fact, most people, for example, in astronomical observer, astrophysicists, addressed these kind of ideas by the term xenobiology, which now is no more used. Astrobiology, in fact, is the study of life in space. I teach astrobiology. It is probably the topic of my teaching which is giving me much more satisfaction. I have a lot of students. Every year I have like 150 students in my course, which is an optional course. So I could have 0. But in fact, I have a lot of them. And most of them are biologists. So you see that astrobiology now is recognized by biologists, which is something very nice, something very, very important.
Yeah.
For new, this is the possibility to study something which they would never study otherwise, like, for example, the astrophysics of stars, even the structure of the atmosphere and the origin of life. You also have courses about the origin of life, but sometimes you don't have. If you have a course in astrobiology, you can learn a lot about the origin of life.
Yeah. So yeah, well, we know basically that life, at least on Earth, is centered around carbon, right? So we don't know other forms of life, I think, that are not carbon-based. So do you think, maybe it's a bit of speculation, but do you think it's possible to have other forms of life? And do you think life in general is something that is common in the universe? So the universe naturally had to develop life, or is it something very rare?
Okay, let us start from the beginning. Okay, this is one of the most important topics in astrobiology. Okay, not really in terms of the practice of the research in astrobiology, but if you open a book of astrobiology, you find this problem exposed in the very first pages. So, for example, which is the chemical nature of life. Mm-hmm. Now, the problem with life is that we only have the life on Earth. Yeah. So it is a strong limitation. You know nothing about life in space because we have never seen life in space, not even a past life like fossils. You have nothing about this. So you have not the faintest idea, in fact, about the possibility of life out of Earth. Now, people say, the universe is so impossibly mind-bogglingly huge that there must be life somewhere, okay? But if it means, for example, okay, in the excess of negativity, that if it means that we have maybe another instance of life out of our galaxy, in practical term, we have life only on Earth, okay? Because we don't know how it is. We know very little about the origin of life, so we have complete different possibilities, and you can argument about the validity of these ideas, like in a trial. Scientists do this when you have really at the beginning of the discipline. You can say, I have very good scientific reasons to believe that life in practical terms is only on Earth. Or another colleague may say, I have very good evidence, indirect of course, evidence that life is very common. Maybe on Mars there was life, not now, very common. Almost on any time you have appropriate condition, you have life. Let us imagine that life is commonplace. Now there is the problem. Is life similar to Earth or completely different from Earth? So maybe, for example, could life be based on silicon instead of carbon? Mm-hmm. And now, this is something of which you may elaborate. At least this is something which you may elaborate.
Yeah, I remember
because we have yes.
I remember this study, I think not so long ago, where they detected some molecules in the atmosphere of Venus, and they thought, this molecule can be only produced from forms of life, so they were imagining these sort of forms of life like fluctuating the atmosphere of Venus. Phosphine, exactly. But that would be a form of life that is totally different than the one of Earth,
Oh no, this is astrobiology. This is the kind of astrobiology which becomes very well known to a wide public. Yes, this is astrobiology. Now, the problem about phosphine in the high atmosphere of Venus is that phosphine is very simple. I wrote in fact a simple account, not for specialists, about this, and it was more than 1 year ago. They asked me to write this just after this discovery. And I was more on the negative side, but still I am. It is very difficult that you may have a bacteria in the high atmosphere of Venus. It's not impossible, but the problem is one of the lessons which we have learned by astrobiology, we don't have life, but now we have a lot of study about the evidence of life, how to evaluate the evidence of life. So, for example, phosphine is a molecule which on Earth is produced by life. You don't have, or they are negligible, non-biological processes which are able to produce a phosphine. But in fact, the phosphine is a very simple molecule. Phosphine is a pH 3, 1 atom of phosphorus and 3 atoms of hydrogen. So it is quite possible that in space we have chemical reactions, not on Earth, which may produce this molecule, because this molecule is a very simple molecule. So maybe we don't understand in all details the kind of chemical reaction which may occur in the high atmosphere of Venus, and we have to understand this before assuming that we have found bacteria which maybe are not necessary to produce such a simple molecule. You know, these molecules are called biomarker, which means molecules which probably are produced only by life. And so if you find them, probably you have life. But I don't believe in very simple biomarker. I don't believe, because now we know that even oxygen, we know now that even oxygen may be produced by inorganic processes. Even oxygen. If you have a simple molecule, you can produce it in a lot of ways. In my opinion, a biomarker would be, for example, chlorophyll. This would be quite strong evidence. And even chlorophyll can be produced by inorganic method.
Okay. So if you have to bet, for example, what's the chance that in the next 10 or 20 years we find strong evidences of life on other planets or satellites or whatever?
In my opinion, if life is common in the universe, we may discover life even next year, because now we have the technology. Now is a very good time to study astrobiology. Now astrobiology is going to perform a transition from speculation to practical science.
Okay.
But if life is not commonplace, so it means that there is nothing to find where we are looking for it, then we will not discover it.
Okay. Okay, maybe one last question, one last comment to conclude. Also, that is also related actually to the aim of this podcast, that is really the communication of science to a general public. I think really that the perception that we in general as a population have of science is very important, especially now that we are in this COVID area. Unfortunately, have some trust on scientists and on science. I think is very, very useful. And the way we communicate is not optional anymore. We need to communicate in a good way, I think. So what do you think about that, about science communication? Also for younger people, younger students. So you're being interviewed also by journals, local journals or television and so on, and you teach. So what is the importance of these outreach activities? And how can we improve that actually?
Contrary to some of my colleagues, in fact, I don't believe that at the moment we have a lack of communication. Okay. In the last few years, most of my colleagues got into the conviction that it is nice to be known by a larger public. So there is a lot of communication of science. Now I believe that we have a problem of quality. Yes, quality now, in my opinion, is more important than the quantity, because the young people and even the general public, they are able to select. They are able to choose. So now we must be, it's like when you look for a book and you go to the public library or the bookshop and you want a book about plainness, and you have a book, plainness, and I know most of these, so you don't buy another one. I know most of these. So then you get a book which is very original. For example, some idea about, I don't know, how rocks are connected with the atmosphere in the context of plainness. Okay, I am just thinking about. Okay? So maybe you say, oh, this is something about plainness I wanted to know. So in my opinion, what we need now is to avoid to produce other 20 books about planets, if we already have 20, and to think about what people want, okay, if they want to make another step, because they want to. Now is not like 10 years ago or 20 years ago. General public, I believe, knows a lot about science. Now we must give them something which is more advanced. And you must be able to do it. You must be able to communicate it, because it is not so difficult to communicate basic science or to communicate qualitative concepts. But are you able, for example, to explain which is the role of a mathematical speculation in the context of chemistry? Now, it is even difficult to find an editor for a book of this kind, because they are they think that maybe they don't sell that much. And in my opinion, we need a lot of a more advanced dissemination, as a divulgation, but more advanced. People can have more. For example, if you ask to editor, I want to write a book about this topic, they say, okay, please, no chemical formula, no mathematical formula. This I think is wrong. It is no more the time of this, and they don't sell, maybe because people want something more. They don't find, they don't buy.
That is true. That is true. There are a lot of, actually, probably there are more ways to communicate. A lot of people can communicate now, but it's the quality of the communication that we should stress on.
Yeah, we must reach a higher level. For example, I have friends of my friends, which are not expected to know about science, but for example, they are able to answer correctly to a significant fraction of my astrobiology, of my text, or the test of my exams in astrobiology, because they learn a lot about astrobiology and about space on the TV. They're very, very good. A lot of information. A lot of people know about Venus, about Mars, and even about plasma. So now you must, you may assume that they know something. You must go to the next level. You must not be afraid to go to the next level.
Yeah, okay. Okay, Savino, thank you very much for being here. It was a pleasure to talk with you. And
Thank you.
see you soon. Bye-bye.
Bye.